Hi, I wish to welcome you to today's lecture on queuing theory, one of the techniques in operational research. In this topic, we want to learn a few things. We shall start by looking at the definition of what a queue is and try to understand what queuing theory as a concept in operational research is all about. Then we shall look at the various components that make up a queuing system. That is basically the structure or elements that make up a queuing system. And some of them will be the arrival distribution, departure service distribution, the service channels, the service discipline, the maximum number of customers that can be allowed in that queuing system, the calling source of customers for that given system, then the customer's behavior. So these 7 elements are the components of a queuing system that we should be interested in discussing in this lecture. Then we shall be looking at the operating characteristics of a queuing system. Then finally, we shall look at types of queuing systems. There are various types of queuing systems, but in this lecture, we shall be looking at a specific one, a particular one, where we talk of a single channel queuing system, so that we know the assumptions behind it, the structure, and even how to solve real-life problems which assume a single channel queuing system. But we shall also mention other existing queuing systems before that. So to begin, we define a queue as simply a line or a sequence of people, or could be vehicles or any other item, waiting to receive a given service. So they are waiting for their turn to be attended to or to proceed to the next level. That's a queue. You'll all agree with me that we encounter queues almost on a daily basis of our lives. We encounter queues of vehicles, maybe queuing to get a service, maybe in a petrol station. We encounter queues of people, maybe to receive a service, let's say admission at university or admission in a school. Parents and students make a queue. We encounter queues even when you're going to a hotel to get to be served food. You make a queue and so on. So queues are omnipresent almost in every sphere of our lives. And so it's important that we study the waiting line of these behaviors that we meet on the queue. And so that brings us now to this unit, or this topic, queuing theory. So in queuing theory, we are simply studying the waiting line. And we are saying the waiting line could be consisting of maybe one or several customers waiting to be served. Because optimization as a technique, queuing theory as an optimization, then there is something that we are either minimizing or maximizing. And so in queuing theory, we are interested in at least minimizing both the waiting costs and the service costs. Now, the waiting costs are costs incurred by customers while waiting so that they get the service. So if you can quantify that process of waiting in terms of costs, we talk of waiting costs. And then the service costs are the cost now incurred by a customer while receiving the service of the counter or being attended to by whoever is providing the service at the facility. So these two costs is what we are actually interested in queuing theory. So in queuing theory, we can say the total cost is actually the sum total of waiting costs and the service costs. And these are the costs that we are interested to actually minimize or get the optimal cost that actually we can optimal cost, at the same time making sure that we provide the quality service that is needed. Now, you realize that a graph of maybe showing the expected cost and the level of service, so that you have a graph of expected cost in operating a facility against the level of service on the x-axis, you'll find that as the service cost increases, also the service level improves. You can see the cost of providing the service is actually directly proportional to the service level. So as the quality of the service improves, then it means that you are spending something more to provide that service. If it is a facility, probably you have employed more tellers. So if you have employed more tellers, we expect the service level to improve, or you have employed more cashiers, or maybe you have used some training and so on, training of those cashiers or workers. So that is a service cost. And so we see it also increasing the quality of the service. At the same time, we see that as the waiting cost reduces, also the service level improves. But you can see at this particular point, let's say when the waiting cost is so high, we see also the poor service level. The service level is so poor. And so we are trying to play around with this cost such that we're able to minimize the total cost, which is now the cost of providing the service plus the waiting cost. And so we seek to find an optimal service level, a particular service level along this x-axis that tries to minimize the sum of this waiting cost and service cost. And so the sum total of this cost is what we are now calling the total expected cost that is represented by the broken line. And so the minimal one, which is now the optimal one, for this case is actually that particular point. And so when you look at the corresponding value of the service level, you get it at this particular S. So this S will be the optimal cost. This is the optimal cost that actually has corresponds to the minimum or the optimal. This is the optimal service level that corresponds to the minimum total cost. And so we shall be seeking to make sure that we find this total expected cost that gives us the optimal service level in waiting in queuing theory. So then we look at the components of a queuing system. We have already mentioned them. And so in this, we are looking at the best practice out there in queuing system. When we look at arrival distribution, we are looking at the pattern in which customers arrive at the facility to get the service. And so this pattern kind of follows a particular distribution. And so if it's assumed that the arrival rate is always random in a real world business, or in a real world business world, arrival rate is random. And so if it's random, the customers arrive in no logical pattern over time. But we are told management scientists have demonstrated that these random arrivals of customers at a facility in a queuing system can be best described using a Poisson distribution. We know Poisson distribution is one of the discrete statistical distribution that has only one parameter, typically denoted as lambda. And so it is the distribution that we use to model the pattern of customers arriving at a facility to receive the service. So one unique thing again about a Poisson distribution is that a Poisson distribution usually has its mean equals to variance. And so the distribution is e raised to negative lambda raised to x by x factorial. So that is the PDF of the Poisson distribution. So it's a distribution with only one parameter among the very few distribution with only one parameter. So that's the distribution we shall be using to model the arrival pattern of customers at a facility for most of the queuing problems. Another element that makes up a queuing system is the service distribution or the departure distribution. And here we are talking about distribution that represents the pattern of customers leaving the facility upon receiving a service. So once they have received the service, at what rate are they leaving the facility? And so in this case, we now model the pattern of service distribution, or the pattern of customers leaving the facility using an exponential distribution. An exponential distribution, now this is a continuous distribution. And so it's assuming that the system is not idle at all. It is busy throughout. That's why we are having customers leaving the facility continuously from the start of the system to the end. So we use this exponential probability distribution. Again, this has also one parameter, just like the Poisson distribution. Then service channels. So any queuing system, as part of the components, we should be able to define the service channels it uses. Now, we are saying under service channel that it can be a single service channel, or it can also have a number of service channels. By single means, I'm having just customers queuing on one line, and then we have a server or a service provider at the end of it all. So one queue and one service provider at the end. But you can say we can also have a number of service channels. So for example, we can still have parallel service channels. Some customers queuing on one line, another one on the line, and the lines are parallel. And we have maybe also several service providers at the end of it all, so that people line, let's say A gets served by this customer, and the others on line B get served by this particular service provider. It is also possible that even the service channels are also series, particularly let's say an admission process in a school setup where we have, yes, the queue is just a single one of customers, but we have service providers at intervals. So like, let's say customer service provider one will only be checking maybe the documents, the ID, maybe the birth certificate, and maybe the KCC certificate is an admission to university. Then now moves to the second, maybe service provider will be maybe checking the medical documents. Then I'll go on, check maybe the next one, maybe looking at the units, maybe registering, and so on until the entire end of the process. So those are the kind of service channels we are talking about. So whatever queuing system, it must be able to elaborate and define the queuing service channel it uses. Then the service discipline of that facility must also be captured as part of the elements or components that makes it a queuing system. And by service discipline here, I'm talking of the order of service or the rule by which customers are selected from a queue for service. We have facilities that use the common disciplines like first come, first served. And yes, maybe they are served customers based on their arrival time. And then so others use last come, first served. You'll find even others use just random service in random order, and depending with what you want, the service you want to receive. Others use priority as an entity, so that they are serving people maybe with special needs, or people are sick, people are elderly, so on. But what I know is that most facilities will actually have a blend of, let's say, priority and first come, first served as the most common. They use first come, first served as the domineering rule of order of service, but then they allow special cases of individuals when they come in, if they have special needs, to get the service first. But the rule, you'll find that is actually first come, first served. That's the most common one. Number 5, you're saying a queuing system must also define its capacity, the maximum number of customers that can be allowed in a system. We know that some facilities only a limited number of customers allowed in the system. And so new arriving customers may not be allowed to join, maybe after a particular number has already registered. And so that means that any queuing system, then the capacity must be known. And we are saying this can be finite or infinite. Some systems can allow as many as they can. Others have a limited number of customers that it can actually serve at any given period of time. Then the next element, number 6, you're talking of the calling source or the source of the customers. And the queuing system should also be able to state this. But the arrival pattern of customers depends upon the source that actually generates them. So you're saying that if only a few potential customers are only available, then we say that the calling source is actually a finite. If there's a few, that means you can actually count them. But if there are many potential customers for that particular queuing system or facility, then the queuing system is said to have an infinite calling source. And you'll find that any number over 40 may be treated as actually an infinite source of calling customers. Then customers' behavior, which is also important in queuing theory, because the type of customer behavior will influence even the mathematical calculations that involve the waiting line. And so what are these customers' behavior we are looking at when you are studying queuing theory? There are basically 3 characteristics. There's bulking, there is reneging, and there is joking. Those are the 3 characteristics whenever we are talking of customers' behavior as a component of queuing system that we discuss. What this means is that what these terms mean, that bulking means a customer arrives at the facility to receive the service, but fails to enter the queue because the queue is probably too long and decides to leave without joining the queue. And so in that case, we say the customer has exhibited the behavior we call bulking. We say he has bulked or she has bulked. So a customer fails to enter the queue at the facility just because it is very long. Another characteristic of customers' behavior we have said is reneging. Now, what reneging means here is that a customer enters the queue, but after some time, he or she loses the patience and leaves the facility, loses the patience. This happens in most queues in the real world. So some customers, because maybe they have some other engagements elsewhere, they thought they could take maybe a shorter time at the service facility. So when they join the queue and realize that maybe they are taking too long or the queue is not moving as fast as they expected, they leave. So you say the customer has reneged. So that characteristic of reneging. Then the third characteristic is what you're calling joking. And joking, as this happens mostly when we are having multiple queues or multiple channels providing the service. So when there are 2 or more parallel queues and customers keep moving from one queue to the other, probably, of course, a customer will decide to move from line A to line B if he observes that line B, the cashier is actually, or they are serving fast and the line is moving pretty fast. Then a customer may decide or opt to move from line A to line B if at all the service that the service providers are providing is actually the same. So that behavior of customers moving from one queue to another is what we are calling jockey. So we say the customer has joked. So those are the components now of our queuing system. Now, let's look at now what are the characteristics of queuing system. And characteristics, we are just looking at terms and that involve queuing system that will even help us now in doing some calculations by considering the simplest queuing system that we call the single channel queuing system. So we want to define terms that characterize the queuing system. And these are terms like the queue length, the system length, the waiting time, and so on. And of course, the associated notations that come with it. So when you talk of the length of the queue or queue length, basically denoted as LQ, we are talking of the average number of customers in the queue waiting to get the service. The average number of people waiting on the queue, waiting to get the service. For example, when you get into a bank to get the service, you always get a ticket, and the ticket will be telling you how many customers are ahead of you before you. So maybe say 20 customers. So that will be the number of customers waiting to get the service. But you are saying this excludes those already at the serving point, those already who are being served at that particular time. So we are only talking of those already on the waiting, not those with the cashier or with the teller if it's a bank flow. But when you talk of system length, the system length now is the average number of customers in the system, in the entire queuing system. So we are talking of customers on the waiting line plus customers at the service point. So the two sum up what we are calling length of the system. So those ones on the queue plus on the service. Then the waiting time in the queue. The waiting time in the queue now, the time you are spending while waiting before you get the service. So that's the waiting time, the average time for which a customer has to wait in the queue to get a service. So if you have told that you have 25 customers before you, the 25 customers is actually the queue length. But if they tell you that you have 20 minutes to wait before you get the service, so the 20 minutes is actually what you're calling the waiting time in the queue. The time you have to wait on average before you get the service. We are saying on average because these are usually estimated quantities. Then the total time in the system. Now the total time in the system, just like the length of the system, this would now be this will now be the waiting time on the queue, the time you wait on the queue, plus the time you spend at the service desk while getting the service. So the two sum up to what you're calling the total time in the system. And then the utilization factor, which is normally denoted as rho, we talk of the proportion of time the server actually spends with the customers. The proportion, that means a proportion. Proportion means a value between 0 and 1. It's like a percentage. Server actually spends with the customers. And it's also called the traffic intensity. Traffic intensity. So those are some of the characteristics that actually describe a queuing system. We have seen the components of a queuing system, and we have seen now the characteristics. Now, we need to have a special mention of the various types of queuing systems. And we have what we call the single channel queuing system. We have saying only one channel and one server. And then we have multiple channel queuing system. We'll have 2 or more servers or channels. We have what we call single phase system and multiple phase system. Sorry. So these are some of the various queuing systems that we have. Now, to be able to appreciate those characteristics of queuing system that we have just mentioned, we are now going to look at a single channel queuing system in detail, discuss it, its assumptions, and even work out some problems involving single channel queuing system, so as just to be able to understand what queuing problems look like. So a single channel queuing system, sometimes denoted as just MMI, looks like this setup. We have one channel and one server. You can see the entry point of customers, which are saying customers arriving at the system. So from a particular source out here, and you can see some of them already making a queue. We have several customers making a queue, one long queue, just one channel. And then we have one server or one cashier or one teller. So once you get the service, there is an exit from the system or a departure point. And so we have only one channel and one server. That's basically what single channel queuing system is all about. And so maybe we look at the various assumptions that this particular model considers as very important. So one of them is that arrivals are served on a first come, first served basis. You know, this is mentioning, but the assumptions, most of them, they talk about the elements of a queuing system. So like we talked of one of the elements of a queuing system being service discipline. And so you can see the service discipline that's adopted by single channel queuing system is first come, first served basis, which sometimes they just denote it as FIFO, first come, first served. Then we have every arrival waits to be served regardless of the length of time. We have talked of customers' behavior, bulking, reneging, and joking. So in other words, under the single channel queuing system, that this system assumes that there are no behaviors like reneging and bulking. So that means any customer who arrives at the facility has to persevere, stay on the queue until gets the service, even if the service is slow. So these are now the assumptions or weaknesses when you're working out this. So there's no reneging, there's no bulking. Another one is that arrivals are independent of preceding arrivals, but they change over time. They change over time. Just to say that the arrival rate is random, you can never, there's no logical pattern of customers arriving. And then we are saying the arrivals are described by a Poisson probability distribution. So we are describing the arrival distribution. And for most queuing problems, the Poisson probability distribution will be used most often. And apart from just that arrival distribution, they're also saying that the source of the customers is actually infinite, a very large population. Then we're also saying that the service times also vary from one customer to the next and are independent of one another. One customer might spend more time at the service desk than the other, but the average rate is known. The average rate is known. Even the average arrival rate of customers is also known. So those are assumptions. Then we also say the service time occur according to exponential probability distribution. So we are modeling the rate at which the customers are getting the service using exponential probability distribution. And then the average service rate is greater than the average arrival rate. Now the average service rate, we shall be using mu to denote the average service rate, and the arrival rate, we shall be using lambda. So we are using mu as a parameter of exponential distribution and lambda as a parameter for Poisson distribution. And so for us to use this single channel queuing model, we are saying mu must always be greater than lambda. then only one server and one waiting length. Yeah, that is just to mean single channel, and then and single server kind of model. So these are the assumptions of a single channel queuing model. Now, once you have known that, we now need to look at those characteristics of queuing models, but in this case, characteristics of a single channel queuing model, and see how we can be able to define those characteristics more explicitly in terms of the formulas associated with it. Already, I have said that we are using lambda to represent the average arrival rate and mu to represent the service rate. But then we are saying that for us to make use of this single channel queuing model, then the mean mu, that average service rate, must be greater than the average arrival rate. So the first characteristic of a queuing model, like the average waiting time in the system. Remember, we are saying this is the time on the queue plus the time on the service. Is actually denoted as WS and is given just by the reciprocal of the difference between mu and lambda. So that's how we calculate using that formula. So once we know the average service rate and the average arrival rate, we can actually estimate the average waiting time in the system, the queuing system. Then the second one, we are talking of the average waiting time on the queue. The average waiting time on the queue, of course, must be less than the average waiting time in the system. So it's a proportion of average waiting time in the system. And so if it's a proportion, what proportion is it? It's actually lambda over mu of the average waiting time in the system. Remember, lambda is smaller than mu, and so this is just a proportion. So a proportion of the average waiting time in the system. So if you were to substitute what the average waiting time in the system is, then we should be able to see this equation to come in clearly. So it's a proportion lambda of mu of WS as the average waiting time in the queue. Then what's the average number of customers in the system? Remember, these are customers on the queue plus customers at the service point. So those are the average number of customers in the system. And you're saying this is given by simply the arrival rate of customers times the average waiting time in the system. So we are getting this as lambda of lambda WS, or lambda and divided by mu minus lambda as the average number of customers in the system. Then the average number of customers in the queue, again, this is a proportion of average number of customers in the system. And that proportion is actually the same as the proportion of average waiting time on the queue compared to the time in the system. So you still use lambda over mu of LS, where L is the average number of customers in the system. So the relationship is more similar between time and the number of customers. Now, we may also be able to predict the probability that the queuing system will be busy. That means if it's busy, it means it's going to have a queue throughout, and there is no immediate service. So this is given by lambda over mu. The probability that the queuing system is actually going to be busy. We look at the arrival rate, and we also look at the service time rate. So that proportion is what gives us the probability of a system being busy. Now, when you now want to talk about the probability of a queuing system being idle, that means at some point having no queue, then we are talking of the complement of being busy. So that's just, if P is the probability of the queuing system being busy, then 1 minus P becomes the probability of being idle. So we get it as shown in equation 6. Then the probability of exactly n customers in the system. You may want to predict the number of customers in the system to know the probability. Let's say, as a probability that there are 20 customers in the system. Then this expression comes in handy when you're trying to predict that. Equation 7 will be very useful for that. And then the probability of more than n customers in the system. Then this is the formula that we are going to use. So the n greater than a particular integer k, which is a whole number. So just if k is 10, just insert 10, and this will be 10 plus 1, 11. Of course, lambda and mu must be defined and must be known at the beginning before you make use of any of the formulas that we are stating. And then the probability of less than n customers in the system. We now have use again, just modify the same equation. Probability of n less than k is 1 minus lambda over mu raised to k. So those are the formulas that define the characteristics of a single channel queuing system that we have to make use of whenever we are actually discussing about a single channel queuing system. So let's have an example here and see how we can make use of that. The example talks of Dr. Mary is a dentist who operates a dental clinic at the city center. We are told patients arrive at the clinic at a mean rate of 20 patients per hour. The consultation period taken by Dr. Mary per patient is on average 2 minutes. Each patient is allowed only one consultation per day. And so this question, when you read it keenly, we are only having one server who is Dr. Mary. That is the only one who is serving patients. So, and then patients are getting in to get the service. So I'm assuming, so the patients are the customers. So even if it has not been mentioned as we assume a single channel queuing system, if it's not mentioned, you'll always assume it's a single channel queuing system. But somehow, even when you read the narrative, you get to know that in this case, there is only one consultant who is now like a server or a cashier, and the customers are now patients who are making one queue. And of course, it's the imagination of everyone that the customer, the patient who arrives early will be served first, so we'll see the consult first than the other. And so with that assumption now, we now look at when they talk of patients arrive at the clinic at a mean rate. So that means they're giving you the arrival rate, the number of customers per hour, the number of customers per hour. So you can see lambda is 20 customers per hour, 20 customers per hour. So that is the arrival rate, lambda. So even if they have not mentioned that you are modeling the arrivals using Poisson and the service time using exponential, it is assumed. If we have assumed a single channel queuing system, then we know the assumptions that come with it. So then we need the service rate. We have been told something here that the consultation period taken by Dr. Mary per patient is on average 2 minutes. That means one patient is served for 2 minutes. Now you can see that for every 2 minutes, one patient. And you have said for every 1 hour, 20 customers arrive at the facility. It's always good to make sure that the rate of lambda and the rate of mu is actually in same units. So if the rate of arrival is in terms of customers per hour, it's also good to change the service time here to be the number of patients served in an hour, so that then the units are uniform to be able to carry out the mathematical problems associated with this. So we need to know how many patients will be served in 60 minutes. That's equivalent to 1 hour. And so this is now going to be 1 times 60 divided by 2, and this gives you 30 patients or 30 customers per hour. So that means I'm talking of customers are served, 30 customers are served in an hour. So that way, you have defined your lambda, you have defined your mu. It will be very easy now for you to carry out any problem associated with the characteristic of this sorry, queuing system. Now let's look at a problem now, like find the average waiting time in the system, the average waiting time in the system. Now, once you have seen this formula that the waiting time is given by 1 over mu minus lambda, and you have defined your lambda to be 20 and your mu to be 30 in terms of hours, then it will be easy for you just to substitute and get this as 1 over 30 minus 20. And this will be now, because this is in hours, it will be 1 over 10 hours. Now, if you want 1 over 10 to change into minutes, just multiply by 60, and you see that this is also equivalent to 6 minutes. But still 1 over 10 hours is still a valid response. Now, what's the average waiting time in the queue? The average waiting time in the queue, we say, is a proportion of waiting time in the system. And the proportion was lambda mu of whatever you have found here. So lambda mu of 6 minutes, or lambda mu times 1 over 10, because lambda over mu is actually 20 over 30 times 6 minutes, you get 4 minutes. So what this means is that a patient arriving at Dr. Mary's premise will spend 4 minutes waiting on the queue. But then we are told the patient will spend 6 minutes at the facility. So what this in a nutshell means is that 4 minutes will be on the queue or on the bench waiting line, and 2 minutes will be now maybe seeing the doctor during consultation. So that now the total time spent at the system being 6. And so we can see how we get those two, the average number of patients in the system. So on average, how many patients are in the system? We say these are patients in the system. We are talking of patients on the waiting line plus patients now receiving the service. So that one, a patient, the doctor, and this one. So if there are only two, it's like you're saying there will be, at any given point, you'll be having one patient on the waiting line and one patient with the doctor receiving the consultation. And again, you just use the formula and you're able to get it right. The average number of patients in the queue, yeah, the patients in the queue, like we could easily tell even before that is given by this formula, and we are getting a value of 1 point something, which you are saying the number of patients or customers can never be, must be a positive integer. That's why we have actually translated one patient. Then the probability of that queuing system for Dr. Mary being busy is actually given by lambda over mu. So it's 67% chance that she'll actually be busy while providing a service. And of course, the probability of being idle is just a complement. So 1 minus 67% to give us 3%. Then the probability of exactly 3 patients in the system. Once you have the formula, you can see all the formulas involving queuing system. They make use of lambda and mu. So unless you know the lambda and mu and you have defined it correctly, then you will not be able to answer these questions. So lambda over mu, then the k, now k, we are talking of 3. We just substitute, and the rest you make use of a calculator. So you're saying the probability of exactly 3 patients in the system is 0.1. So we have already seen that the probability of the number of patients in the system is 2. So the chances of having 3 patients in the system is actually small. Then the probability of more than 3 patients is still small, you can see. And the probability of less than 3 patients in the system is actually 0.7. The high chances that you have less than 3 patients in the system. The previous example, we say that there are actually 2 patients, and at any given point in the system, 1 on the queue and 1 at the service point. So that's why you can see the probability is much higher compared to the probability of more than 3 patients or exactly 3 patients in the system. Another example could be this one of cars arriving at a drive, and you're told they're arriving at a rate of 4 for every 10 minutes. The average service time is 2 minutes. And you say we are using a Poisson distribution to model the arrival rate, and we are using exponential distribution to model the service time. So suppose you wish to answer these questions, the average time a car in the system, the average time the car spends waiting to receive the service, and the average number of cars. So you can see that here, if you want to know the average rate, arrival rate, we want to know lambda. You see that 4 cars are arriving in every 10 minutes. So you can say, let's say in 1 hour, how many cars arrive? And so you'll be talking of 4 times 60 over 10. And so this means that lambda is actually 24. So you're talking of 24 cars per hour. So that can be your lambda. Then the service time is 2 minutes. That means we are talking of 1 car gets a service in 2 minutes. So let's see how many get the service in 60 minutes. So this would be 60 times 1 over 2, and this gives you 30. So that means we are talking of the service time here is actually 30 cars per hour. So once we have these two, we have the lambda and we have the mu. It now becomes easier for us to calculate any form of question. Like, for example, what's the average time in the car as part A dictates? We now just talk of, this is just going to be 1 over mu minus lambda. And since we have said mu is 30 minus lambda 24, you get this to be 1 over 6. And 1 over 6, those are hours. So if I want to convert into minutes, 1 over 6 times 10 times 60 just gives me 10 minutes. And so for this question, I've given you responses for each bit. So you can still again use the same formulas for single channel queuing model and just verify that the answers I've given in blue actually tally. So that is how we work out questions on this. That's how we work out questions on single channel queuing model. Thank you so much.